Our lesson today is on molecules, the small molecules, to determine whether they're polar or nonpolar. We're going to check what group number they're in on the periodic table, and we're going to check the symmetry of them. Because remember, if symmetrical molecules have equal forces going in all directions, there will be no shift of electrons, thus no charges, therefore nonpolar. So let's get started. We're going to look at linear molecules, bent molecules, trigonal molecules, and tetrahedral molecules. Let's get started. So group 2 will be our first group we look at. That'll be the group of beryllium, magnesium, calcium, and elements like that. All molecules we'll look at are bound with hydrogen. So what do we mean by group 2? We mean that the central atom is going to be coming from group 2. So the example I want to do is beryllium to hydrogen twice. Okay, well, if we're in group 2, that means we have 2 dots, and then we will spread the dots out as far away from each other as possible. We'll put one here and one on the other side. Just as a gentle reminder, remember the atomic orbital would be 2 dots paired. But when we do the orbitals that are for the covalent molecules, we will spread them out. So then I'll attach my hydrogens at these 2 locations here. Okay, thus it is a linear molecule, and here's our model of it. The green represents the beryllium, and the 2 whites represent the hydrogens. And this is totally symmetrical. Okay, therefore there will be no net charges on this molecule, and therefore nonpolar. Let's go to the next example. We're going to go to group 16. All the way over here, we find oxygen, sulfur, selenium, tellurium, polonium in that group there. Group 16 has 6 dots. And the example we're going to do is water, H2O. And like I said, all examples in this lesson will be done with hydrogen, just for simplicity's sake. Okay, now oxygen then, with 6 dots, there's no more places to put them, so we will have 2 dots paired, one by itself, and then one by itself. We will then add the hydrogens at these locations, one here and one here. That's the dot diagram for it. And it correlates with a bent-shaped molecule. So group 16 makes bent-shaped molecules. We have extra electron dots here that are not actually being paired in terms of a compound. In other words, no hydrogens are bound there. Okay, therefore, this is an asymmetrical molecule, and there will be charges. In the extra electron location, we will have a negative charge, and on this part here, we'll have a positive charge. We don't have equal forces, therefore we'll have extra electrons over here, and we'll have a negative and a positive. This is polar. So group 16 make asymmetrical molecules. Let's go on. What about trigonal planar molecules? Well, these come from group 13. Group 13 has 3 dots. And the example we're going to do is boron to hydrogen 3 times. Now, a reminder that boron would be 2 dots together and 1 dot by itself, and that would be for the atomic orbitals. But since we're making compounds, we'll have boron like this, and we'll spread them out equally, and then we'll add the hydrogens on them. So we'll put the H here, and put the hydrogen here, and put the hydrogen here. So we look at this molecule will be completely symmetrical everywhere. And if you look at it, it looks like this. It's called trigonal planar because it's flat. This molecule has 120 degrees between everything. So it's completely symmetrical, therefore nonpolar. So group 13 makes nonpolar molecules, and they all make trigonal planar molecules. Let's continue. Another example. What about trigonal pyramidal? These come from group 15 elements. Okay, group 15 includes nitrogen, phosphorus, arsenic, antimony, and bismuth in that group. Okay, these have 5 dots in group 15. And the example we're going to do is ammonia, NH3. And when we do ammonia, we will have 2 dots together, one by itself, one by itself, and one by itself. There is nowhere to spread those out. So we go like this. I'm going to put the hydrogen here, the hydrogen here, and the hydrogen here. Now one more time, we look at this molecule and we see that it does lack symmetry, therefore asymmetrical. If we look at it, instead of being flat, it's kind of got a pyramid shape to it. The extra dots are here as compared to right here in the flat diagram. Okay, so this is the actual molecular geometry of it, drawn using the program. So because it lacks symmetry, we have electrons left over here, and we don't over here. We're going to have a negative charge here and a positive charge on this side of the molecule. So that'll be polar. So we come to the conclusion then, if there are extra electron dots, okay, that are not actually bound to an atom, we're going to see that the molecule is asymmetrical and indeed polar. Our last example is going to be the tetrahedral molecule. The example I want to do there is methane, CH4. Okay, that would be in group 14. Group 14 includes carbon, silicon, germanium, tin, lead, and that group there. Those all have 4 dots. Now remember, the atomic orbital would be 2 together, 1 by itself, 1 by itself. We will spread all those out so that we have 4 equal corners. And now I will put the hydrogens on in these locations here. 1 hydrogen here, 1 hydrogen here, 1 here, and 1 here. That correlates to symmetry everywhere, so that's a symmetrical molecule, and here's what it actually looks like in 3 dimensions here. That's called a tetrahedral molecule. And it is nonpolar because, again, there's symmetry everywhere. So again, anytime you don't see extra electron pairs that aren't being bound to an atom, you'll have complete symmetry and therefore nonpolar. And that's how you handle determining whether or not something will be polar or nonpolar. Really, it looks like there's only 2 groups that end up being polar then. That would be group 15 and group 16. Everything else is nonpolar.